Hello students, today we will read about the potential due to a system of charges. Initially we have seen the potential due to one single charge or the two charges which are in the mutual interaction. Now we are looking at a particular point where few charges, not one or two but more than two charges are acting. So that is known as system of charges. System of charges is where more than two charges act. Okay, so for that we have seen in our chapter number 1, chapter 1, that we found the force on a given point due to system of charges as well as electric field for a system of charges. In these, the main law which we have utilized so far was the Coulomb's law and superposition principle. Superposition principle. So here in this concept of potential also we will be applying our superposition principle as our potential is related with electric field and electric field allows the superposition principle, and hence in this correlation mutualism the potential is also eligible to undergo the superposition principle and find out the principle like the potential due to all these system of charges. For that, doing the calculation and further understanding how it is happening, we will consider a system of charges q1 q2 up to qn, and these system of charges are at a position vector like r1, r2, rn up to rn. Like q1 is at r1 position whereas q2 is at r2 position. Similarly qn is at rn position relative to some origin, and that some origin is our p's. Check over here, this is our p, that is our some origin. Now the potential v1 at p is given due to charge q1. This is our charge q1. Due to this there is some potential given to p, and that is denoted as V equals to 1 by 4 pi epsilon naught into Q1 upon R1P. Q1 is the charge and R1P is the distance between that particular charge and the point P. That particular charge and the point P. Similarly, we will find the potential V2 due to Q2 and V3 due to Q3. Over here it is Q3 and that should be converted to Q2. So this is what we are getting the equation as V2 equals to 1 by 4 pi epsilon naught into Q2 by R2P, and V3 as 1 by 4 pi epsilon naught Q3 by R3P. Similarly, we will aim at finding Vn for the nth number of charge. So that will be given as 1 by 4 pi epsilon naught into Qn. Due to Qn will be the Vn divided by Rnp, that is the distance. Rnp equals to distance between nth charge and point P. So similarly we can see over here is our R2P and R3P are distance between Q2, Q3 from the P respectively, and so on for many other charges. Now by the superposition principle, the potential V due to the total charge configuration is the algebraic sum of potentials due to the individual charges. We are just going for simple algebraic sum due to the individual charges, and this is given as V equals to V1, V2 plus V3 plus V4 dash 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 up to Vn, because we are considering a system of charges containing n charge. Now for a single charge we have defined it as V1 equals to K Q1 R 1P. Similarly for V2, similarly for V3. Hence we are substituting these values in this particular equation, and the common comes out to be K. What is the value of K? It is 1 by 4 pi epsilon naught. So that is the common value, common of all, common in all. Okay. Now if we have a continuous charge distribution, this is for a discrete charge distribution where we can say this is Q1, this is Q3, Q2. Okay, this particular equation is for discrete charge, discrete charge distribution. Here we can define Q1, Q2, Q3, but when we aim at talking about continuous charge, we have to take the volume. We cannot take single charges in this case. So if we have continuous charge distribution characterized by a charge density of rho of R, we divide it into small volume elements, each of size del U and carrying the charge of rho into del V, that is the charge in a particular volume and density. Then to determine the potential due to each volume element and sum over all such contribution, and thus determine the potential due to the entire distribution. For a uniformly charged spherical shell, this is uniformly charged. Okay, uniformly charged spherical shell, electric field outside the shell is as if the entire charge is concentrated on the center. Thus the potential is given as V equals to 1 by 4 pi epsilon naught into Q by R, where R can be greater than or equal to the capital R. Now what is capital R, small r? I'll explain just a minute. Where Q is given to be a total charge on shell and R is the radius of our shell, and whereas electric field inside the spherical shell is 0, so the potential turns out to be constant. Potential turns out to be constant inside the shell. No work is done in moving the charge inside the shell, and therefore it is equal to the surface. Potential is equal to the surface, that is 1 by 4 pi epsilon naught into Q by R. What exactly is happening over here is that first of all we are just taking a continuous charge distribution, and for taking a continuous charge distribution we will draw one sphere. This sphere is having a continuous charge distribution. This sphere is having a continuous charge distribution like this. The charge is distributed in all the directions of this sphere, but the fact is that the charge is here everywhere. So we will aim at this particular center. At this particular center our charge is concentrated. So due to that centric charge, what is exactly happening is that due to this centric charge, electric field is determined on the surface, and above the surface. On the surface and above the surface. As there is electric field on the surface and above the surface, there is a change in the voltage, and that change in the voltage can be seen as K Q upon R, as R, small r, is the distance from center to the point where we aim to find the potential. Small r equals to distance from center of spherical shell to the point we aim at finding the potential. Finding the potential. So that is the R. Now R can be equal to the capital R. Capital R is the radius of spherical shell. Radius of spherical shell. Now when we are aiming to find this particular voltage, sorry, this particular potential, we inside, what exactly happens is that this E is 0 for inside. The charge distribution inside, if we are taking this as small r, charge distribution can be here also. Uniform can be anywhere, right? It is not exactly in the center. So electric field defined for the for inside point is always 0. Is always 0. So what exactly we aim? Then we will say that electric field inside is 0, hence potential will not change, because as there is no electric field inside, what exactly will happen is we can move the charge freely from here to there to here. There will not be any energy used in doing so, first thing. So as there is no energy used to do so, there is no work done. When there is no work done, no potential is being generated. ठीक है? So if there is no potential generated, the potential will remain constant, and it will be equal to the constant, and it will be equal to the V out. Whatever the potential is outside, same will remain inside. Now one trick to remember which value out of E and V will remain constant and which value will remain 0 is that in alphabetical order, E comes before V. So whoever comes first sacrifices. Comes first sacrifices. So E will be 0 inside the spherical shell, whereas V will be constant. It neither increase nor it decrease. Okay, neither decrease nor it increase, so it's constant. V is constant, but E will go 0. So this is an extremely small topic under chapter number 2, that is the potential one, and can be read very easily. It is as same as we have done for the forces and the electric field in our previous chapter, and I hope it's very much understood. These are the basic things just for understanding, and just for the formula we need to read it. There is no such deep concept right now. The only concept which we need to study was while we were doing the forces and the electric field lines. At that time we get to know that superposition principle is a important principle, and which applies to a set of these values, not everywhere. And electric field, potential and the forces are one of the group where our where our superposition principle is applicable. So this concept is done. We'll meet in the next class with the new concept. That's all for today's class. See you in the next class. Have a good day. Bye bye.